Hello, my name is Gerhard van der Horst. I'm a senior consultant to Microptic in Barcelona, and it's my privilege today to present to you this webinar on microscopy with emphasis for spermatologists. I want to start off today by showing you my private collection of microscopes. I'm very fond of microscopy, one of my hobbies, but there's a lot to learn, a lot of principles to learn from this. And so it's not only the fun of the history. So first of all, I treasure these two wonderful microscopes. First of all, this one dates back to the 1860s, 1870s. This is a slightly later model, around about 1890, and you can see they differ from the modern microscopes, and that the fine focusing device was sitting here and not there, as in the modern microscopes. But the one thing that I want to emphasize today is that these microscopes are all built on the basis of optics developed by the German physicist Abbe. Absolutely brilliant man, and you can see here it contains all the basic components. Of course, there was no electricity, so we used they used the light from the sun, and a condenser, and of course the objectives and the optics at the top, and beautiful brass microscopes, all handmade. And I want to tell you a little bit more about Abbe, and perhaps I can just show you first of all that I'm very proud to share an Abbe microscope. This is the one that was actually used by Abbe, made by Zeiss, this of course is Professor Abbe, and I just want to show you here how important he was really considered. In Germany, they especially had this wonderful stamp developed, the Deutsche Bundespost, whereby they commemorated Abbe, as you can see here, from Zeiss in those days, and this was the inscription on his grave. But why was he such an incredibly important man? And the reason is mainly because of the fact that he has developed this theory, which is absolutely long-lasting. It is the resolution limit engraved on Abbe Memorial in Jena, where Zeiss was, or still is. And this is the whole principle of light microscopy. And it tells us something about the resolution. Resolution means the smallest distance that you'll be able to distinguish between two objects. So that would stand for resolution, that the wavelength of the light, and this 2 alpha. And this long formula I will allude to later on, but basically that relates to the numerical aperture. And I can assure you that in all these microscopes, all these old microscopes, they don't indicate magnification on these objectives, but the numerical aperture, because that's more important. It tells you how you will be able to distinguish the smallest distance between two objects. And I just want to give you an example how little things have changed optically, and how little things have changed in terms of the minimum resolution limit that we can actually find. And I'll just show you here one of the most remarkable people by the name of Gustav Retzius, a Swedish scientist, who, that is Gustav Retzius, and he has studied the sperm of some 400 species with a resolution level or a detail that nobody even today can comprehend. Look at this here, and I will increase the magnification a little bit for you. And this is how Retzius in 1904, with a microscope like I've shown you, an Abbe microscope, could see a rat sperm with this incredible amount of detail, with the acrosome here and there, even the connecting piece with the tail. And only in the late 1960s, 70s have Don Fawcett actually with electron microscopy shown us these details that Retzius has remarkably seen already in 1904. So this is really an important point. And so what am I telling you? And the basic home take message here as a starter is simply that already by the late 1800s we have already accepted Abbe's concept that the minimum distance that you will be able to resolve an object, that you will see something, was already determined. And even despite the most stunning advances in microscopy up till now, 2020, we cannot exceed the maximum resolution limit of a numerical aperture of 1.4, because that boils down essentially to a spherical lens, and you can't get more spherical than spherical. So it was great that Abbe has actually determined that already more than about 170 years ago, that is the minimum distance that you'll be able to distinguish two objects from each other. So this really then ends off this very first section, and I will now show you greater detail in the modern microscope. Several times I have promised you to get back to the concepts of resolution and numerical aperture. So let me do it by means of this absolutely wonderful web page of Nikon. No wonder they call it the source for microscopy education. It's really absolutely excellent, and I can refer you very strongly to this. I'm going to use this as probably the best example to explain the question of the limits of resolution, which is related of course to numerical aperture. So every bit of an image can be explained in terms of an airy disk. So it is a series of diffractions that take place, primary, secondary, tertiary, etc. So every little bit of an image that you see actually can be represented as what we call an airy disk. When airy disks overlap, we cannot distinguish between two objects. When they are far enough from each other, they are resolved. And this is how it would look three-dimensionally. What is the physics again involved? And we have explained that to you in terms of Abbe's idea of the numerical aperture. And let's just take it back to this point. If we have an image which is where the object is very, very little small particles, for example, subcellular components of a sperm cell, then we will not be able to resolve it at a numerical aperture of about 0.2, which is about 10 times magnification. And so if we increase the numerical aperture as in a 100 times objective lens, then you can see the airy disks do not overlap. And if I can just show you, you can see the intensity of the airy disk is very high, and we can clearly distinguish one point from another point. So what is the physics involved? It is resolution is again lambda, the wavelength, over 2 times the numerical aperture. And I showed you that numerical aperture is also related to the acceptance angle of that particular lens. The bigger that angle, of course, the bigger the numerical aperture. So I think the one thing that you've been waiting for all the time is, so what is actually the limits that we can see at the different magnifications? And here you can very, very clearly see that, for example, with a 4 times lens, you only have a numerical aperture of 0.1. So you can only distinguish objects that's around about 3 micrometers in size from each other. Whereas with a 10 times, 1.1. So sperm cells are about, human sperm is about 5 micrometers by 3.5. So easily we resolve it with a 10 times for swimming sperm. And also for morphology, you can see when we want to start to see more detail, yes, we get down to this. And of course, 100 times, we are almost down to the size of a mitochondrion. So I really hope that this little section on the relationship of resolution and a medical aperture assists to make you understand how important these concepts are and what you are able to see under optimal conditions. To be able to get to that situation of ideal resolution, we really need to follow very, very specific procedures in setting the microscope up. And the person who has really been instrumental in developing the optics for this at Jena also, and again working for Zeiss, was Professor Keller. And Professor Keller has actually come forward with this very unique system. And it looks complicated, but I'll try and make it simple. This is your field diaphragm. This is your condenser, your objectives, your ocular in the end where you view. So this is the light path. And you see here we have two light paths. Let us first consider the one with the red arrow. And I think it is really crucial that we understand that it is not only required to sharply focus the objective on the image, but also to focus the light sharply on the image. If you overfocus or underfocus, a lot of photons get lost and does not contribute to the image. So it's very important to set up your microscope according to what we call critical illumination, which forms part of Keller's illumination. And so those light waves that contribute towards the image refer to critical illumination, whereas the parallel waves cause an even background illumination as indicated here by blue, not passing through the image as such, but along the image, and so providing a really even lit image. It's very important in image analysis that we have that situation. And let me show you a very nice, again from Nikon, interactive. Often when a student starts and they open the microscope and they look, they don't see anything. And there's just a little something here. This is an example of a Graafian follicle, and this is the optical field. So what is the first thing you need to do? Well, open your condenser aperture a bit. Okay, so there's something. Open the diaphragm a little bit. Oh my goodness me, it is totally decentered. So what you do is with the two centering screws, you try and get it right in the center. Then the next thing is you focus your specimen, and then, very important, you now find the correct condenser, and you can make this a little bit smaller to see it better. You can find the correct condenser setting, and here is one where you see the very sharp edges of the fish eye, and that means now that the light coming from the light source is sharply focused on the image. You can now open up your condenser and you can perhaps increase the aperture and just look at that immaculate image shown with this really nice demonstration. I'm going to, in this part of the webinar, just very, very quickly review the basic components of the compound microscope. Of course, the lighthouse here, which contains a tungsten lamp. Here is the field diaphragm that directs the light via the condenser lens to the objective, and eventually, of course, the image is seen here with your oculars. And for recording or for image analysis, we need a trinocular tube and a camera that relates it via USB 3 to a computer program. But of greater importance now is to focus a little bit on these inscriptions on the lens. It's surprising how many scientists work with microscopes and they can't tell you what these inscriptions mean. And first of all, Yes, of course, the 10 there refers to the magnification. But if you ask most people, what does that 0.25 stand for? They don't know. What does that pH1 stand for? What does this BM stand for? What does that WD stand for? And these are really important points. They're not just inscribed there for the fun of it. It is really functional. So let's start with it then. 10 times the magnification, 0.25 refers to the numerical aperture. And that is the whole basis of microscopy. In the sense that tells us what the acceptance angle is of this particular lens. The greater the acceptance angle, the higher this value, and accordingly the better the resolution. So this is the numerical aperture, and I will later on show you a formula relating numerical aperture to resolution. That means the smallest distance that we can distinguish one point from the other point. The pH1 here refers to phase contrast. So we can do ordinary bright field microscopy with this lens also, looking at stained slides. But with phase we can look at, of course, live tissues without staining them. And this is just in this instance to show that it's BM, it's a negative phase contrast, but we also get positive phase contrast. This is a very interesting inscription here, and you can see there's a line, an infinity line and a backslash or a forward slash and a minus sign. It actually shows that we don't need to use a cover slip of a specific thickness. In the older microscopes it would indicate 0.17, meaning that you need to use a cover slip of that thickness. But I recommend still very strongly that that is the thickness of cover slips you buy. And this just refers to the wide angle that you will be able to see at least a certain number of millimeters. So this then concludes the very first part of this introductory section. In the previous video I showed you phase contrast microscopy, whereby we, through contrast differences in light, we actually visualize the image. In other words, we don't need any staining and we can work with live tissues. But here is a very advanced system called Nomarski differential interference contrast microscopy, whereby we can actually further enhance contrast, even to the extent that the images are almost produced in 3D, and I will later on show you some of these 3D images. So while this is a much older generation microscope, I just need to show you again. Similarly, it has a lighthouse condenser lens, just very fancy condenser lens in the sense that it contains so-called Williston prisms, which actually separates the light into direct and indirect beams. And here we have very special little filters which actually helps to enhance the diffraction. And we work with polarized light, so we have a polarized filter here at the bottom, one here at the top, and in the end we see a most amazing 3D effects through Nomarski differential interference contrast. This is an introduction to fluorescence microscopy. Today, this is absolutely central in research and even in clinical practice, and through fluorescence microscopy we can use specific labels and very specifically identify different components of a cell and even what it consists of. For example, we can in sperm cells use specific fluoroprobes by which we can identify the acrosome and do the acrosome reaction, and it will just produce fluorescence of the acrosome. The principles I will later on explain, but in a nutshell it boils down to the following. In 1852, Sir Professor Stokes developed the concept of the Stokes shift, which means that when you use ultraviolet light, which has one wavelength, the diffraction effect, or the effect that comes back, is at a different wavelength. So while we cannot view ultraviolet light with the naked eye, we get the fact that that is converted into what we call the visible spectrum. Okay, so let's go over to the components of the fluorescence microscope. The heart of the fluorescence microscope are three components. First of all, this very high voltage, high pressure mercury lamp, which is driven by this particular unit here, and we work in an interesting fashion which is called epifluorescence. So this very high beam of energy is transmitted all along here past so-called neutral density filters through a particular cube here, which actually I will show you the details just now, which contains very specific lenses to control the wavelength in which we are going to work. Then the very special quartz lenses. And this mode of sending the mercury beam in this direction is called epifluorescence. And so the light that is diffracted back is what we will see from, or depending on what happens in this particular area. Let me show you how one of these cubes actually look like. And you can see in this instance we have here an excitation filter, and inside we have a dichroic mirror which reflects the light down or absorbs the light, and then at the top we have the barrier filter. And you can imagine now, by controlling the wavelength here of light which will go through, that will only excite within a very specific range of wavelength, nanometers. And then when the light is diffracted back, which is now visible light, this barrier filter again narrows it down to a very specific wavelength. These cubes can become extremely complex in the sense that it can serve, for example, two different kinds of wavelength, both, for example, in the blue range for FTSE, for example, and then in the red range, for example, for Texas red, where we can do things like mitochondrial membrane potential. So these are the absolutely central components: your mercury light, your cubes which control the wavelength, your quartz lenses. That forms the heart of fluorescence microscopy. In the preceding section, I've given you background on bright field microscopy, phase contrast microscopy, Nomarski differential interference contrast microscopy, and fluorescence. And the ideal would be to show you all the optical principles involved and all the components and the role they play, so that you really understand what is actually happening to the image and why you see differences in contrast. But we simply don't have the time, and I only have time really today to show you what's happening in phase contrast microscopy, because that is the mode in which you will operate most of the time as spermatologists. So let's go directly to it. And here is the setup in a typical phase microscope. You can see that is now the lamp, the condenser, objective, and so forth. So what is different from bright field? We have this condenser annulus, which actually allows the light to come through as a cone of light. The light only passes through there, and that cone of light is lined up to this faceplate which sits in your objective lens. And the faceplate consists typically of two parts. It has a part which light can pass, undiffracted light can just pass straight through these areas, but there where the actual ring is, that ring, it either stands out as in negative phase contrast, and in positive phase contrast it's like a furrow. So here is a very, very nice example of how this actually works and how the waves are actually, what happens to the waves. And you can see that after passing through the phase annulus, it interacts with the image, and of course that light which is diffracted from the image would actually go through either the thicker part in negative phase or the thinner part in positive phase. And the non-diffracted light would go straight through this thinner part. And you can see it creates these contrast differences. If I move this slowly, very slowly, you can see that in bright field mode, we barely have, between the green and the red, we barely have any contrast, and we will see virtually nothing of live tissue. On the other hand, if we move slowly to positive phase contrast, you will see that we now deal with the light out of phase in several areas, so that we will see quite a lot of subtleties and quite a lot of detail of the cell that we would not otherwise have been able to see. Whereas with negative phase, you've seen is more geared towards really big contrast differences. So I hope that this helps a little bit to give you a little bit of better understanding of what the phase microscope is all about and how it actually operates. This is then our very last section, and we're going to start straight away now with the final part, which involves actually showing you all these microscopic techniques. It's one thing to talk about the theory, but it's another thing to do it properly. So in this instance, 3 Tanqua goat sperm, and you can see beautifully analyzed with a microptic system. Why? Because the background is even, the staining is good, so we're adhering to all the good principles. And here you can see further horse sperm, elephant sperm, human sperm, each time the sperm here being stained with sperm blue, and every time you can see how it's been analyzed in each instance. But please notice the even backgrounds, the sharpness of the images, and how clean it is and how even the illumination is. Killer illumination, Abbey principles. I cannot overemphasize how important that is. And this is bright field microscopy again, negrosine, eosine showing the live sperm in white, the pink sperm in red, swelling occurring in the live sperm. And here is an example of positive phase contrast microscopy. And you can see here that we see the individual sperm very nicely, the background is very even, and all the prosthetic particles, etc., appears in black. So how did it analyze? And here you can see that it's really analyzed well. It didn't analyze any of these background particles, which is really great. And negative phase contrast. Here again, there's a huge contrast difference between the sperm and the background. And see how beautifully you can see this. Notice the even background illumination. Notice the sharpness of the sperm. And here is the actual analysis that you can clearly see how well the sperm are actually analyzed. Here is another example of negative phase contrast microscopy, where we have showed you a very difficult example of, in this instance, hyperactivated Tanqua goat sperm. And if your optical conditions are not perfect, you will never, but never in your life get such a good analysis, as you can see here on the right hand side. Nomarski differential interference microscopy. I told you that this is the 3D, almost like scanning electron microscopy for the light microscope. And here is ferret sperm, domestic ferret sperm with a smooth posterior border of the acrosome. In the black-footed ferret, it is scalloped, and it's an excellent way to actually show these differences that you otherwise would not have seen. And this is sea urchin sperm, really nice small sperm with a little midpiece and a tiny tail, also really showing up very nicely. Again, notice the even illumination and the sharpness of the images. And finally, fluorescence microscopy. Here, human sperm with acrosomes, Fitzy filters that we used here, and you can see how beautifully we've labeled the acrosomes here and how well they fluoresce using the appropriate filters. This is from Dr. Liana Maria's work showing the mitochondrial membrane potential with the mitochondrial part in deep red, and here the head, the nucleus, with Horst staining and a Dalby filter. So absolutely perfect conditions. And here again Tampa goat sperm, but here we've also used Horst staining so that one can also see the nucleus. And this is just to show you with Dalby staining one can do cell cultures and get beautiful fluorescence out of it if you do it properly. And finally then, all that remains for me is to say thank you to Dr. Rita Kotze for the assistance with video photography in our comparative spermatology laboratory, and my son Maximilian van Horst, who has assisted greatly with the video editing. That then brings us to the end, and I really hope that you have found something out of this that is useful for you, and I wish you the very best. Goodbye.